Yeah, good day. Welcome back to my online class. Today I'm on the shear stress in beams. So this shear stress that we're talking about, uh, you can call it the horizontal shear stress, or you can call it horizontal shear stress, or you can call it transverse shear stress. So I'll just show you where is that coming from. But in general, we have the vertical shear stress and the horizontal shear stress. Right. So let's say you can take rulers, maybe three of them or four of them, or plank, or the anything. So let's say we have a beam like this, made of maybe three planks or three pieces of woods like this. You arrange them like this. So after this, you apply force here. So when you apply force there, we expect this to bend. So when they bend, they will go like this. They will go like this. Oh, sorry for my drawing. Uh, maybe let me just restart it. So due to the force, this will bend. Yeah, at least. So if you take those rulers of yours and then bend them, you are going to have something like that. So you will see that as those rulers bends goes down, uh, they will slide over each other. So as they bend like this, as you can see there, there will be scratching here. Those things, rulers, they will be scratching each other like that here. They will slide over each other. So as you can see, this black line is almost horizontal. So that means there will be a force created between those surfaces. That force will be acting in this direction. So because there is a sliding there will be that scratching force or that sliding force. Then we know that scratching force or that sliding force, we call it the shear force, and then the shear force which will result with the shear stress. So the shear stress or the shear force that we're going to calculate in this chapter is all about this. So which will be created by the bending. So as you put the load on this beam, whether it's a cantilever beam or simply supported beam, either like this is simply supported beam. If you put the load there, we expect this beam to bend like this. So it will bend like this. Then if you put your rulers like that, they will go like that. So as they bend, they're going to scratch over each other like that. So between these surfaces of this ruler, there will be that sliding force in between, which is the shear force or the shear stress. Remember, the stress is just the force acting per unit area. So shear stress is a shear force. Shear force you're acting per unit length or per unit area. Right. Now back to our question, or let me just give some formulas that we're going to use uh, along the way. So why are we calculating the horizontal shear stress? So we have to find the horizontal force or the magnitude of the force that will be generated here. So that magnitude of the force that will be generated here, we're going to call it the shear flow. So we're going to give it the symbol Q, which is the shear flow. So what is the shear flow? The shear flow is just the shear force that will find per meter length, for 1 meter length. In other words, the shear flow is going to give you the magnitude of the force that you are going to find on this beam, which is having a length of 1 meter. Remember, as this thing bends like this, as it bends like that, there will be a force generated here. There will be a sliding force generated. So this total force that you see with these arrows here, this force that will be created here there for 1 meter length, the amount of force that we are going to find for 1 meter length, that force is going to be given by this Q, which is the shear flow. So to calculate this shear flow, you can just use the normal formula that you know, like force equals to shear stress multiplied by the area. So remember, we know how to calculate shear stress at any point from the previous lesson. So from the previous lessons, we know that the shear stress at any point would be given by this general formula, which is V, which is the the shear force or the shear stress. We're calculating shear stress. V stands for shear force, then multiplied by Q, which is the moment area, first area moment, over I, second moment of inertia, multiplied by B, which is going to be the width of the beam. So if you want to know that shear force or that shear flow, which is the force, you will just have to take this formula here, this one. So you replace this shear stress by this one here, then you multiply it by the area. So the area is going to be, okay, you will say F equals to shear stress, you use VQ over IB multiplied by area, which is going to be the length. The area is going to be this. It's going to be this side multiplied by this side. So this side is going to be the length, but it's going to be 1. So we're going to consider 1 meter length. So then here is going to be B, the width of this beam starting from here to there. We can call it B. So the area of this part here is going to be B, this side, B multiplied by the length. So here, instead of the area, you can say B multiplied by length. Right. So the length, since I said that we're going to consider 1 meter length. Actually, this beam, I can say, is quite long. It continues like this. Continued like this. It's just that for calculation purposes, we don't know the length of this beam. It continues like that. So we don't know the length of this beam, but for calculation purposes, we're only going to consider 1 meter length. 1 meter length. So that's why here this L is going to be 1. And then this B will divide this B. Then shear flow or Q, remember this thing here, it's Q, will be equals to, will remain with VQ over I. So that's where this formula of the shear flow is coming from here. So the unit is going to be Newton per meter. So since we said that length is going to be 1, so that means the force that you get here, the amount of force that you get here is going to be the amount of force for 1 meter length from here to there. So that's why it's going to be force per meter length for 1 meter length. That's why we have 1 here. Right. We're going to find this force that will be generated here in between. The force that will be created here as this beam bends. Why are we doing this? Is because we're trying to find, okay, first of all, we don't want this thing in our structures. We don't want this thing to slide. We don't want this, it can be the planks or it can be any material. We don't want this thing to slide over each other. So to prevent this thing to slide over each other like that, we have to put some nails, or we can put the rivets, any jointing material, or you can use glue in between here. You can use glue, or you can weld. You can weld these things. So now, before you choose the method that you're going to use to join these things, you have to find the magnitude of the force that will be created here as this thing bends. So to find that magnitude of that force, we have to calculate this. So this thing is going to tell us the amount of force, how big is this force that will be created here. So once we have this, then you can choose or you can find the size of the bolts. Obviously, if the force that will be created here is small, then you don't have to use the thick, you don't have to use thick jointing material like nails. You don't have to use the thick nails. So if the force in between is small, which is this Q here, if the Q is small, then you have to use the smaller size. Your nail must have the smaller diameter. But if the Q is big, then the diameter of this thing has to be big. The same thing as well, the number of bolts, it depends on this Q. So if the force that will be generated here is going to be too big, then you'll need more bolts or nails. Then you can put more like this. You can put the nail there, nail there, nail there, nail there. But how many or how much you'll need, then it will depend on this force that will be created, which is this Q. So that's why it's very important to calculate Q first. Then from there you can decide using the professional knowledge whether you're going to use a few bolts or many, or are you going to use the thick one or the thin one? It all depends on the Q. Right, so at some point we're still going to calculate the pitch. So if you put the nail here and nail here, we don't just put the nails anywhere. So if you put the bolt here along this line here, so we don't just put the nails as you wish. We have to calculate the pitch, the distance between this nail and this one, the distance between this one and this one. So this thing, we're going to call it a pitch. P. You can use the symbol P. I think some authors will use the symbol S. So now to calculate this distance or this pitch, we're going to use this formula. So the formula will be like this. If you use S, symbol S, you will have S equals to C multiplied by N over Q. So this Q that you see here is the very same Q as this one, which we will calculate using this. And then this N. This N, let me write it here. This N will be the number of bolts per pitch. This N here is going to be the number of bolts per pitch. Let me go back to this. Remember, you will have a pitch. Remember, in general, it's just a distance from one point to a corresponding point. So let's consider this. Let's consider this from here. I thought I've changed. It's fine. So from here to there is still the pitch. From here to there is still the pitch. Okay, let me start drawing something. So if you have a beam like this is the top view of the beam. So from the top, it will be like this. Now, so now the pitch is the distance from here to there. From one point to corresponding point is the pitch. But for us, we are not going to use that. It's still the pitch, but we are going to use this. When I'm talking about pitch, just know that you will be talking about this distance from here, from this point, then the corresponding point is going to be this. So this distance in between here is going to be the pitch. So when you check here per pitch, you are going to find how many bolts? You are going to find the 2. So you are going to find 2 bolts, which is this one and this one. So when you go to the next pitch, from here to there, you are going to find the 2 bolts. So this N here, just be careful of it. This N represents the number of bolts per pitch. So it's not the total number of bolts. This is not the total number of bolts. It's just the number of bolts per pitch. But as well, it will always be equal to, you can get it like this. It will always be equal to the number of rows. It will always be equal to the number of rows. So as you can see here, per pitch we have how many? Per pitch we have 2 bolts. And then when we check the rows, when we check this is row 1, this is row 2. How many rows do we have? We have 2 rows. So that's why I said that this number here, it can either be the number of bolts per pitch, which is the right way, but it will always be equal to the number of rows. So if you have 3 rows, like here, if you put bolts there, bolts there, bolts there to join those rulers or planks or whatever, if you have this like this, you'll have 3 rows. 1, 2, 3. But at the same time, if you consider a pitch, if you consider this pitch starting from here to there, when you check this pitch, how many bolts are you having? You have 1, 2, 3. So if you have something like this N will be equals to 3. That N will be equals to So this C that you see there, it represented the resisting force in the bolt. The resisting force in the bolt. Yeah, so remember some authors here, they will use R, the resisting force in the bolt. So it will just depend on the author. But it just represents the resisting force by the bolt. So remember here I said that we don't want to see this sliding here. We don't want it to see this. We don't want our material to slide over each other. So to prevent that sliding, it means that we have to put the fasteners, let's say the bolt. So if you put the bolt here like this, as this thing starts to bend, the material will be pushing like this. We'll try to push this bolt like this. And then this bolt has to resist. This bolt has to resist, must push in opposite direction. So it must make sure that due to bending, as this thing will be pushing in this direction, the bolt must apply force in opposite direction. So let me draw a bolt like this. So due to this force here, which is the shear flow that will be generated here, as this thing bends, without the bending, this force won't be there. So as this thing bends, which is the force that will be generated here, there will be a force pushing in that way. So this force is going to be Q. Then to prevent this kind of step here, this bolt must push, must react, must push in opposite direction with the same magnitude. So this force by the bolt, I don't know, we can use R, we can use that C there. So for this thing to be at the state of equilibrium, this force by the bolt, which is that R, it must be equals to that shear flow. So in order to have the balance, this force, which is that shear flow, must be equal to this force, meaning that as the bending occurs, there will be a horizontal force generated. Then to prevent that sliding, this bolt must apply the same force in opposite direction. So now this C that you see here is the reaction force by one bolt. So remember, we're going to have maybe a bolt like this. We're going to have bolts like this, like this, like this, like this, like this. So this C, it represents one bolt, this one. That is the shear force of one bolt, or the resisting force of one bolt. So now the reason we have N here, we have this N, is because we don't want, sorry, back to full screen. Yeah, on this formula here, we don't want the strength of one bolt, but we don't want the resisting force of one bolt. We want the resisting force per pitch. So as you can see here, per pitch, if you want to find the resisting force per pitch, then we take the resisting force of one bolt multiplied by 2. Since per pitch here we have 2 bolts. So that's why you're going to have this force, this C, which is the resisting force of one bolt, multiplied by the number of bolts per pitch. So meaning that these two bolts, they're going to push in opposite direction with this magnitude. That's C multiplied by N. So just be careful of that. Now, this force due to the bending, which is the shear flow, you will calculate it using this. But the resisting force, we are going to use this. Let me shift this thing. Let me find the space here. Let me erase. Let me use this space. Right. So this force will be calculated using this. Then the resisting force by the bolt, F resisting, will be given by this. It's basically coming from this. Normally, they will give you the shear stress of one bolt. And they will tell you that maybe one bolt can withstand this much of the shear stress. Then to find the force, then you just take that shear stress multiplied by the area of the bolt. This one will be the area of the bolt. So, which is going to be the shear stress of one bolt multiplied by pi d squared over 4. So, but this one is going to be the resisting force of one bolt. So now, if you have more than one bolt, like here we have more than one bolt. We have for 1 meter length, let's say from here to the 1 meter. So for 1 meter length, you can see that we're going to have more bolts. So now let's check here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So if you want to know the total resisting force that will be applied by these bolts, then you will take this multiply by 12, which is this n represent the number of bolts, total number of bolts, which is in this case is going to be 12. So this n that you see here represent the total number of bolts per meter length. Total number of bolts per meter length. So just be careful here. This n, it represents total number of bolts, but this one it represents total number of bolts per pitch. This one it represents all bolts that you will find per meter length for 1 meter. So that is the difference. Right. It's not only that. Sometimes you are going to find that we're going to have a double shear. So if you have a double shear, it doesn't have to be double shear, but if you find that your bolt is going to be sheared more than once, yeah, I will show you with the drawing, then you must include this thing. We can use maybe the symbol C. And then this C here, we are going to have C equals to 1 if we have the single shear, and then C equals to 2 if you have a double shear. Right, let me right? Let's say we have two blades like this. Then you put a bolt. It goes like this. Now, when this thing slides, maybe this one will have the tendency of going there. This one will have the tendency of moving forward. Then at this point, this part there is going to experience two opposing forces like this and like that. So this area or this part here is going to experience the shear. It's going to experience the shear. So in this case, if you have two blades like this, you are going to have a single shear. That shear will occur here in between here. In that case, you are going to have C equals to 1 on this formula. This C will be equals to 1. But if you put the third plate or plank or whatever, then you put one bolt like this across. Then in this case, we are going to have a double shear. So this bolt, which is 1, is going to be pulled like this here, and then even here is going to be pulled like that. So we're going to have double shear. We're going to have the shear here. We're going to have the shear here. So this bolt, if it's like this, is going to get pulled like this and like that at this portion. And then at this portion as well, it will get pulled like that and like this. So we're going to have a double shear in this case. And if we have double shear here, then here you are going to have 2. So another formula that we can use to calculate pitch. Remember, pitch is this from here or here. You can call it pitch or spacing. So another formula that we can use to calculate pitch or spacing, it will be this. You can use unit length. Multiplied by the number of rows divided by n. So this n which represents total number of bolts. So the number of rows, if we consider this part here, the number of rows is going to be 1, 2, 3. So we replace this with 3. Then n, it represents total number of bolts. So if you consider this one here, total number of bolts is going to be 12. So you replace with 12 here. So the unit length, and normally we want to know the unit length. We won't even be interested with the unit length. So what we normally do, we always use for 1 meter length. Remember I said that this beam is continuing like that. We don't know up to where. But for calculation purposes, we only consider 1 meter length, 1 meter, and then the rest we forget about. So that's why here always is going to be 1. So we use 1 there. But if you know the total length, you can still use it. But it should be the 1 meter length. 1 meter. Right, that is another formula that you can use to calculate pitch. Remember, this thing started here. Pitch equals to this. multiplied by the number of rows multiplied by total number of bolts. Right. So I think now we have a bit of introduction. Now we can check our problem. Back to our problem. 7.1. You will read that question. 7.1. Yeah, it's too thick. Right. 7.1. You can just read the question. Figure blah blah shown below. Builder beam consists of two channels. You can see we have a channel here and this one here. 260 by 90, that is the size, multiplied by 37.9 kg per meter, that is the density. Placed back to back. So as you can see, yes, channel, yes, another channel. So in this way, they're placed back to back. So sometimes they will say they are placed maybe toe to toe. So if they're placed toe to toe, they will be like this. This is toe, this is toe, toe to toe. So now they are placed back to back, then it's like that, as you can see there. We've got two plates, 300 by 20 bolted at the top and bottom. So as you can see at the top and bottom, we've got two blades, we've got bolts, here's bolt, here's bolt. The maximum shear stress in the bolt is 80 MPa. That is the shear stress of one bolt. The maximum shear stress one bolt can handle is that one, 80 MPa. So if it happens that the shear stress in the bolt exceed this 80 MPa, then our joint might fail. So in order for this joint not to fail, we must make sure that the shear stress experienced by one bolt mustn't be more than 80 MPa. Right. When each bolt has a diameter of 20 millimeter, the bolt spacing per meter length is 200 millimeter. Remember I said that the spacing is what is the pitch. You can call the pitch the spacing. Now, the built-up beam is used as a simply supported beam. We will check that later. Neglect the mass of the beam. So as you can see, this beam will have mass. Remember, when we're talking about the beam now, we're talking about this plate, we're talking about this channel, we're talking about this bolt. So we're going to ignore the mass of this three. We're going to ignore the mass of this bolt, obviously saving the weight or mass, but we're going to ignore it. We're not going to include it when we do calculation. So this plate as well, we're going to ignore the mass. So this mass we're not going to use it. Right now, 7.1, find the number of bolts required per meter length of the beam. So now here we're trying to find the total number of bolts per meter length. Total number of bolts per meter length. Right, now if you recall, I said that this N is the total number of bolts per pitch. Like here for this pitch is 3. This N, this one here, is the total number of bolts for 1 meter length. From here to the 1 meter length. For 1 meter length, how many bolts do we have? Is 12. So the question is looking for this one. It's looking for number of bolts per meter length. So this one is the number of bolts per pitch. So that's why we're going to use this formula. So we're going to use this formula here. And let me write it on this side. So 7.1, we're going to have pitch. I'm going to just use P equals to unit length multiplied by number of rows of bolts divided by total number of bolts, which is N. So now, since we're looking for per meter length, which means this one is going to be 1 per meter length. So we're looking for number of bolts, which is N. We're going to make N the subject of the formula. Then we'll have that unit length number of rows divided by P. So remember I said P is the spacing or is the pitch. So the unit length in this case, we're going to have 1 multiplied by the number of rows. So when you check here, the number of rows, they didn't tell you. They didn't mention the number of rows on this question statement. But right now you just have to, you can just check the drawing. So when you go to this drawing in 3D, it will be something like this. Then this will represent these bolts. These bolts, they will go like that. So by just checking these 2 bolts here, it means that we're going to have 2 rows. We're going to have 2 rows. So they don't have to tell you. You can just check the front view. So when you check this thing from the front view here, you will see 1, 2 bolts. So if it happens that maybe you will see 3 bolts like this from the front view, then that means this thing will mean that the number of rows is 3. So but this time we have 2 bolts here. Then these bolts that you see, they're telling you that you are going to have 3 rows. Oh, sorry, we are going to have 2 rows like this. Row 1, row number 2. You can get that from the drawing. So the number of rows is going to be 2. We got that from the sketch. And the spacing or the pitch, it's given from this spacing 200. So we convert that to meters. You divide it by 1000, you will get 0.2. Then from there, calculator comes in, then you will have 1 times 2 over 0.2 equals to 10. So the total number of bolts we're going to have 10 of them per meter length. So as you can see here, we have 1, 2, 3, 4. And maybe we'll have 5 this side, 5 this side. So for 1 meter length. Remember, the length of this beam is not 1 meter, but for 1 meter length, or for the first meter, we're going to have 10 bolts. So that is 1 mark. That is question 1. I mean 7.1. Now 7.2. Yeah, 7.2, calculate the shear flow per meter length of the beam. That is the Q. So that is the Q. Here we go. It's this one. So to calculate the Q, you have two options. It's either you can use this, or you can use this. Remember, I said that the force, which is the shear flow being applied on this board in that direction, to have the state of equilibrium, the bolt must apply the same force in opposite direction. So the force by the bolt, which is this R or FB, should be equals to the shear flow. So to calculate shear flow is up to you. You can use this formula depending on the information that you have. So you can use this formula, or you can use this formula. Remember, FR or this R equals to this shear flow. Right. Now, when we check at the moment, we don't have some of this information. We don't have I, we don't have Q, we don't have the shear force. I think maybe it's given up there. Then we just have to check between these two formulas which one we have enough information. But when we check on this formula here, we're going to have all the information. So we're going to have shear stress is given as 80. The shear stress of the bolt is 80. Then we have the diameter of the bolt. Now we've just calculated N. Then C is going to be 1. So when we check our sketch here, we only have 2 blades. So if we have 2 blades like this, the shearing will only be okay here. And normally double shear, we have it when we've got 3 blades, or when we have a clevis bolt. From science 4, you will recall that we used to have this, something like this. Then you put a bolt like here, and then your bolt will go like this. Then this bolt will be pulled down here, and then this clevis bolt will pull up. So you will have shear here and shear here. Then we'll have double bolt in that way. Right, in this case, we are going to have a single shear. So another scenario, sometimes you will see this one at the later stage, you will have something like this. Then we'll have maybe ions from this side, equal leg or unequal leg. Then when we check, we'll have this plate 1, 2, 3. So if you pulled your bolt like this here, then maybe this one will push down, this one in the middle pushes up, this one pushes down, this one in the middle pushes up. So this bolt is going to get sheared there and there. So in this case, you're going to have double shear. So with this one of 2 blades, you're going to have a single shear. Now that means we're going to have 1 SEC. So what I've said that is that R or Q will be equals to R. Then we're going to use this formula of pi d squared over 4 multiplied by shear stress, a bolt, multiplied by total number of bolts per meter length, multiplied by C. C is 1 for single shear, and then 2 for double shear. Now we just have to substitute. So when we substitute it there, pi diameter, we have 20 millimeter bolt. Diameter is 20 millimeter. You convert it to meters, we divide by 1000, then we'll have 0.02 squared. Multiply by over 4, multiply by the shear stress, which is 80 is this one. Then I'll have 80 multiplied by 10 to the power 6. The number of bolts we calculated is 10. Then we're going to have a single shear. Then we press the calculator there. Then we get 251 327 Newton. Okay, we're done. So 2 marks for that. The next question, 7.3, is going to be long, and then at some point I'm going to need the sketch. It's fine, I will fit it here so that we can see the sketch. So the most important thing is the sketch here. Yeah, so since they said this is a simply supported beam, question 3 now, they're looking for the magnitude of the point load supported by the beam. So we're going to have something like this. So now we'll have to find this guy here, point load. So from the question, they said that this load is located where? 2 meter. Here we go. 2 meter from one support. So it doesn't matter from which support, from any of these supports here. So it can be from here to there, 2 meter. Then if from here to there is 2 meter, then from here to there is going to be 3. Since the total length is 5. Since the total is 5. So now to calculate this W here, we have to first find the reactions. Remember, traditionally, the way we used to calculate the reactions from science 1, 2, 3, before to calculate the reactions, they will normally give you these loads. So this time we don't have this load. So we're not going to calculate directions the way we used to calculate by taking moments at this point and at this point. So this time we're going to use a different approach because we don't know the load. Right. Now, We are going to use this approach of the shear flow. Let's go back to this formula of the shear flow. Remember Q equals to VQ over I. So actually, let's find this guy. Let's find this one. Then let's find this one. At the moment, we don't have. Then this one, let's try to find it. We don't have at the moment. At the moment, we only have this guy, which is this one here. So we have Q. Let's find the I. Then this I that you see here is going to be I of the whole section combined. So remember, this section is made of channels. Then we've got 2 of them. We're going to multiply by 2. Then we've got plates. So when we check them, we've got 2 of them, and then they are identical. Then we're going to multiply them by 2 as well. So firstly, let's find this I. So maybe we can start by finding I of the channels. I channels. We're going to have, remember to calculate this thing, we use parallel axis theorem. Don't forget that. Parallel axis theorem. But anyway, maybe let's do it separate. Let's do them separately. The I for the channels, you have the size of the channel is this one here. So we go to steel table and check this size, and then find the I. Here we go. Here we go. Here's the channel. Here's that size, 260 by 90, 87.9. Here's our size. Here's our size. So now we're going to draw a horizontal line and go along this. Remember, we're looking for I. So I for this size is this one. The corresponding I is this one, 48.24. That is the I, XX. So it's 48. It's 48 what? 48.24. But remember those properties that you see at the back of the steel table, those ones are for one profile. So this 48 is for one profile. So if you want to know the total resistance of these two, then we have to take this multiplied by 2. So you can multiply by 2 now or at the later stage. Now you may recall that this one here, this is the x-axis of the whole thing, of the composite, this one. This is the x-axis of these profiles combined. So which will be your reference? Remember, from parallel axis theorem, actually you are supposed to have I x equals to I of the channel plus AH squared plus I of the blade plus AH squared. Right. So once you do this, we consider these things individual. We're going to find I of the channel and then I of the blade. So when you go to the channel, we have to check which I are we going to use. Remember, we have IXX and IYY. Each profile is going to have two values of I. It's raining. Don't get surprised with this noise. The room that I'm using is next to the window. Or maybe I have to move. Okay, it's fine. Let's continue. I hope I'm audible. You can hear me clearly. What I was saying is that this thing, this channel, is going to have an axis like this. We normally say parallel to the longest dimension is YY, perpendicular to the longest dimension is XX. So now we want to know which I are we going to use, since we have IXX and IYY. So somewhere here there will be the IXX. This IXX is for the channel. This black IXX is for the whole thing. So this line here that we see here is the same as this one. So to check which one are you going to use here, you just have to check your reference. Remember, we're looking for IXX. So the XX is this black line here. So you go to the channel, then from this channel you check the one parallel. This is parallel axis theorem. You check the axis parallel to this black one. This black one is your reference. This one is our reference, which is this. So from between these two axes, between this one and this one, you check the one parallel to that one. It's going to be this. This XX is parallel to this black XX. This YY, this one, is not parallel. This one is going to be perpendicular. It's going to be perpendicular to this XX here. So we're not going to use the perpendicular one. We're going to use the parallel one. So that's why here from the steel table, we're going to use IXX. From the steel table, you'll have two values, IYY and IXX. So this one we're going to use IXX. We use the one parallel. Then IXX, as you've seen from the steel table, you find that IXX is 48. It's this one. So you can see it's about the XX. Then we have another IYY. It's going to be 3.17. IYY is 3.17, but we're not going to use this one since the axis parallel to that black line is going to be the x-axis. Now we're going to have 248 point, or maybe I should calculate these things separately before I combine them like this. Okay, we're done with I for channels. Then the area of the channel, you'll get the area from the steel table. But this time we won't really need the area since this H is going to be 0. Remember H will be, I will normally say it's Y bar minus Y1. So H is going to be the distance from, or is the difference between the parallel axes. The distance between this XX and then this black XX. So which is, the black XX is this line here. Yes, black XX. So we want the distance between this black XX and this red XX. So as you can see, the black XX and the red XX, they are on the same level. They are on the same level or on the same point. Therefore, there is no height difference between the two. Between the XX, the black XX, and the red XX, there is no height difference. H is going to be 0. Now, this part here is going to be 0. Then we come to the I blade. So blade, we're talking about this one. All right, so we know the dimension of this. This side here is going to be doing 20. And then the other side, okay, here's the dimension. 300 by 20. Here we go. 300 by 20. So meaning that this plate, starting from here to there is 300. Then from here to there is 20. Now, we generally say you don't have to do that. But you can stick to this. I'm not saying that if you do it the other way around, you are not right. We normally say axis perpendicular to the longest dimension. Remember, here is the longest dimension. Between this dimension here and this one, the long one is this. So perpendicular to the longest dimension, we call it the axis XX. And then parallel to the longest dimension, we call this axis YY. So in other words, here we're going to have the axis crossing somewhere in the middle here. We're going to call it YY. Then we're going to have another axis crossing like that, and we're going to call it XX. Now, since we're looking for IXX, then we're using parallel axis. Parallel axis. For the blade, the axis parallel to XX between these two, between this one here and this one. You can see x-axis like this. Then between this and this, YY is the one parallel to XX. So that's why here we are going to have YY. Why? Because the YY axis is parallel to this XX axis of the composite. So here we are going to have YY. So now to calculate I of these plates, since we said we are going to find YY, then I for rectangular profile we use BD cubed over 12. And I normally say that B will be the side parallel to the axis. And then D will be the dimension perpendicular to the axis in consideration. So that axis that we're talking about is YY. So let's check YY here. Let's come here and check YY. Here is YY. So the side parallel to this YY is going to be B, which is 300. This side, which is 300, is parallel to the YY. So B is going to be 300, 0.3 multiplied by D, which is the side perpendicular. Yes, D. This side is perpendicular to the YY. So this one perpendicular, we're going to use it as D, which is 20. Or we can always say that the side perpendicular to the axis in consideration will be raised to the power 3. So we're talking about YY. So the side perpendicular to YY, here is YY, perpendicular to YY is 20. So the side perpendicular to the axis in consideration will always be the one raised to the power 3. Then this part here is going to be this IYY. And then the area will just be this side multiplied by this side. 20 multiplied by 300. H, the height difference. So it's going to be, or you can call it, the distance between the axes. So you check the x-axis of the composite, which is this one. You check the parallel axis, which is this YY. So this difference between this axis here, this one here, this distance is going to be H. We can maybe say it's H2. So this H will be equals to Y bar minus Y2. And Y1 is going to be the distance from the bottom to the center of this rectangle. So this rectangle, you can see from here to this 20. So from the bottom to the middle or to the center, there is going to be 10. So this distance from here to there is going to be Y1. So which is 20 divided by 2, which is 10. And then y2, you have to find this height. Let me erase. Should I erase or should I leave it like that? Okay, it's fine. Let me just continue. Or maybe I should erase it. Let me erase this side only. Yeah, we're looking for the distance from the center here to this center of everything. So remember, from here to there, it's y bar. And from here to there, this distance is y1. So to find this distance here, which is h, you will say y bar from here to there minus this small distance here is going to give you this. So it's simple. If you don't want to use y bar, or let me, since I've started with y bar, to find this y bar, you just have to find the height of everything, starting from here to there, divide by 2. That will be the center of everything, of this thing combined. So to find this total height, you will say this one, 20. From here to there is 20 plus this height. This height from here to there, you will get it from steel table. Then from steel table, from steel table, so the height will be this. So from here to there is the distance that we're looking for. So to get this distance, which is labeled h, you come here and check h. So the h for our size is going to be 260. So then it means this h starting from here to there is 260. So this will be 260. Now total height will be 20 plus 260 plus 20, which is 300. 300 divided by 2. 150. Okay, millimeters. Then you will say 150 minus 10. Y bar minus y1. Remember I said this thing will be given by y bar minus y1. You can say it's h2. h2 equals to y bar minus y1, which is 150 minus 10, which is 140. Or you can simply say the distance from here to here. You can simply find this distance from here to there, which is 260 divided by 2, 130, plus this half distance, 10, 130 plus 10. So it's really up to you. Right, now let us combine everything. So I'm going to follow this formula. So we multiply by 2 because we've got two channels which are identical. We've got two plates. So this I we spoke about it. We said that is 48. Plus area, you can check it from steel table. But I said H will be 0. Then anything multiplied by 0 will be 0. Then we can leave that part. Plus I is this one here. This one. So it's going to be 0.3 multiplied by 0.02 squared or cubed over 12 plus A. The area for this one is going to be 300 multiplied by 20 multiplied by H. H I said is 140. Then when you calculate it there, to save time, I'll do it behind the scenes. You should get 2.08 times 10 to the power minus 6. Right, we move on. Remember, we are following this equation now. We have Q. We just found I. So now let's find Q, area moment. So let's find the Q, area moment. So Q equals to AY. So this Q, remember our point of interest is the joint here. This is where the shearing is going to occur here. So here, this is our point of interest. Here, where we're going to have a joint here. Remember, our bolts will join this top surface and this one here. So now we have to find the force that will be created here. We want to know the shear flow that we will find here in order to find the number of bolts that you will need and the size of the bolt that you need. You have to find the force that will be created there. So that is our area of interest. So now remember, when you calculate the Q, this area is the area above the point of interest. So while you are here, when you check from the top, you will see that the area above this is going to be the rectangle. So area of rectangle, which is that 20 multiplied by that other side 300 multiplied by y bar. So what is y bar? Y bar is the distance from the centroid or the neutral axis, which is this one, which is this. The distance from here to where? To the center of the area above, to the center of the elementary area or the area in consideration. Remember, we're talking about this area. This is the area above. Now, but the center of this area is going to be somewhere there. So we want the y distance will always be measured from the neutral axis, which is from here to the center of the area in consideration. So it's going to be this one, the distance from here to, which is the very same distance as from here to there. These things are identical. We have the axis of symmetry about the x-axis, so the distance will be the same. So you may recall that we said that the distance from here to the center is 140. So we're going to have 140 multiplied by 0.14. Then you will get 840 times 0.14. So in that way, we are done with Q. So meaning that now we can find V, which is the shear force. So let's make V the subject of the formula from this. So if you make V the subject of the formula from this, you will have V equals to Q I over Q. We've got two Q's here. This one is the shear flow, this one is the area moment. So from this, Q from the top we set is 251. I divided by this Q, which is 840. Then V, which is the shear force, will be equals to 99 . So that is V. Right, this is the situation that we have. Simply supported beam, load being applied 2 meters from one of the supports. And remember, this one, it's V, is the shear force. So we're not looking for shear force, we're looking for W, the point load. But before you find the point load, you have to find this reaction. So now we are in the process of finding the reaction. Okay. In general, we know that the shear force diagram of this thing is going to be like this. Remember, they said you must ignore the weight of the beam. If we consider the weight of the beam, we were going to have our diagram, shear force diagram, going like this. But since we're ignoring the weight of the beam, then our shear force diagram will go like this. That's the basic. Irrespective of the magnitude, if you have something like this, the shear force diagram will be like this. Remember, if you have a load like this, it will always be from common sense as well. If the load is placed next to this side, L, let's say we have 10 kN or 10 Newton, and most load will be supported by this side next to the load applied. So load applied is next to the left reaction. So this left reaction is going to carry more. Maybe you'll find that it's going to carry 7 Newton. Then this one, which is far from the load, is going to carry less, 3 Newton. So since this load is 2 meters from the left support, then it means that the left support is going to carry more load compared to this side. So that's why on this side, I went up, knowing that the reaction on this side is going to be more compared to this side. That's why this side is long, this side is short. So it's because of that. So once we have the shear force like this, then starting from here to there represent, this is the shear force diagram. It represents the shear force. The shear force from this point to this point is represented by this. The shear force from this point to this point is going to be smaller. It will be represented by this. So remember, starting from here to there, we were guided by what? By the reaction. If the reaction is 5, then we move from here to there by 5. Then we move horizontal like that. Then it means that from here to there as well, this is the shear force diagram. It means that on this beam, starting from here to there, the shear force is going to be 5. Like I said, if the reaction was 5 here, let's say, let me just take an example. Let's say the reaction is 5 Newton. Then we draw a line like this going up 5 Newton. Then you draw horizontal line, meaning that the shear force is constant, it doesn't change. Meaning that the shear force from here to there is going to be 5. So in this kind of scenario, the shear force will be equal to the reaction. So meaning that, as you can see here, the shear force is 99. The shear force is 99.358. Then this shear force will be equals to this reaction here. It's going to be equal to this reaction. So it's not always the case. You must understand that. It's not always the case that the shear force diagram will be equal to the reaction. It's just that this one is not that complex. That's why we can, from the general understanding, we know that we go up here by the magnitude of the reaction. And as you can see, this line, this height, starting from here to there, it represents the shear force. And then this V, it represents the maximum shear force. And then this beam is going to experience the bigger shear force on this part. Then how much is the shear force on this part? Is this much. We're not going to use the shear force of this side. We always go for the bigger shear force. We don't use the shear force of this side. That's why we're not even interested with the shear force on this side. We use the big one. So this value here always represents the maximum shear force, which is going to be this side. Then this shear force here will be equal to the reaction. So in other words, the reaction of this side will be equal to the shear force. The reaction is going to be 99.358. That is the reaction here. So now once we know the reaction, we can find the load. So to find the load, you can simply take moment here at point R. So let's take moment at point R. We know that clockwise moment equals to anti-clockwise moment. So when we are here, clockwise moment is going to be this force, which is that direction force of 99.358 times the distance is 5. From R, from here to there, it's 5. Equals to anti-clockwise. Anti-clockwise, you will have the load, point load, which is what we're looking for, multiplied by the distance from R to there, which is 3. Then from here, W, which is the point load, which is what we're looking for, will be equals to this 99 times 5 over 3. Then you'll get 165.597 K. It's K because this value is in K, remember. So that will be your final answer, 7.3. Yeah, thank you very much. If you have any question, you might ask it in the comment section. Thank you very much.